Nuclear Energy, Key to Tomorrow. Produced by WQED for the Educational Television House Electric Corporation and the Atomic Energy Commission. The subject, history. Your host, Dr. Warren Witt, Manager of Reactor Physics, Bettis Atomic Power Division.
Hello, my name is Warren Witzig. I'm your host in this series of discussions on nuclear energy, the key to tomorrow. In this discussion today about the history process, the process which makes the uranium in these bottles so valuable to all of us. Today, we're especially privileged, for we have with us an outstanding historian of science, a man that has been awarded Pulitzer Prizes, the second one for his recording of the history of nuclear energy. This man is the science editor of the New York Times, and he has such a fabulous and interesting story to tell you that without further ado, I'm going to introduce to you Mr. William L. Lawrence.
Thank you, Dr. Ritchie. I consider it a privilege to be here, and I'll try to tell you the story as briefly as possible, though it's a long story.
Fine, Bill.
We really will begin with an unknown young patent clerk in Bern, Switzerland, about the beginning of the century, working for about $600 a year, at the same time working on a theory that revolutionized man's concept of the cosmos in which he lives. The name of the young patent clerk is Albert Einstein. The name of the theory is the theory of relativity. In that theory, there is a little formula which every schoolboy by this time has learned. It's called E equals mc squared. But this formula revealed for the first time that the two great entities of which the material universe is made, namely matter and energy, instead of being two separate entities, are really two different manifestations of one and the same entity. That matter was really energy in a frozen state, just as ice is water in a frozen state.
Mm-hmm.
Whereas, on the other hand, energy is matter in a liquid state, the same way as water, you might say, is ice in a liquid state. And then he found out, by means of this formula, that each amount, a small amount of matter, freezes within itself a tremendous amount of energy. I'll illustrate it by means of a dime. The dime, this silver dime, equals about, in weight, 2.5 grams. If the 2.5 grams could be unfrozen and converted wholly into energy, they would yield the equivalent of 62 million kilowatt hours. 62 million kilowatt hours represents the labor of 620 million adult, strong, young human beings working for a whole hour.
That's a tremendous amount of energy,
That's a tremendous amount of energy. But when he reported it, it was more only of academic interest, because nobody believed that man would ever find a key to tap that tremendous amount of energy, which later was known to be the energy used by the stars, by the sun, the energy that keeps life on Earth going, but we did not believe it would ever be possible to release it on this Earth. Now, the fission process, the story of the fission process is really the story of how man, at last, you might say, stumbled upon a key to that great treasure house of energy, which until then only the sun and the stars could use. And that begins really, again, sometime around early in the 1930s, in 1932, a young British scientist named James Chadwick discovered a second constituent of the nuclei of atoms. All atoms, as we know today, are made up of three major constituents. Electrons and protons are the two charged particles. The electron is in the shell of the atom, very light, and carries a negative charge of electricity. The proton is much heavier than the electron. It carries a positive charge of electricity. The charges are equal. The negative and the positive are equal, so they balance each other, and the atom as a whole is neutral. But until 1932, we did not know that the nucleus of the atom also contains a neutral particle. The neutral particle has the same weight as the proton, but it has no electric charge. Therefore, it was called a neutron. And so the nuclei of all atoms, in which more than 99% of the matter and the energy of the universe is concentrated, the nuclei of all atoms consist of protons, positively charged particles, and neutrons, neutral particles. And they are surrounded by electrons in a shell or outer several shells, depending on the size of the atom, which go around, revolve around the nucleus like the planets revolve around the sun. So we have really, in all atoms, a miniature solar system. Mm-hmm. Now, as soon as the neutron was discovered, another young man, of whom the world later was to hear a great deal, but at that time unknown, his name was Enrico Fermi. Enrico Fermi was that time working at the University of Rome. And he was 31 years old. And he immediately realized that because the neutron had no electrical charge, it could penetrate the electrical barrier around the atom and also would not be repelled by the positive charge in the nucleus, and therefore could be used really as the veritable philosopher's stone for which the alchemists in the Middle Ages were seeking in vain in order to find a means to transmute base metals like lead into precious metals like gold and platinum. And so Fermi started, he made for himself a tiny little vessel. Oh, it's made of glass. It was about an inch long and about less than maybe an eighth of an inch in diameter. And inside that vessel, he put a little bit of radium and a little bit of beryllium. And the radium shoots out natural bullets, and it hits the beryllium. The beryllium releases neutrons, and then Fermi used these neutrons to fire away at other atoms, doing what the alchemists did, changing the elements one into another. Mm-hmm. And he finally came to the last element of all, namely uranium. Uranium has got 92 protons in its nucleus and 146 neutrons. That's the heavy part of it, the heavy form of uranium, and was the last element in nature. It seemed as though the Creator, when he created the world, said, we'll stop right here with 92 elements, that's enough. And so Fermi said, by means of this neutron, we really could continue the work of the Creator. I'll now take uranium, and if I fire which has a weight of 238, and if I fire a neutron which has an extra unit, I will have an element weight 239. And if I fire two neutrons in it, I'll have an element weighing 240 or 241. So he started doing it with that little philosopher's stone that he made for himself. And everything went along fine until he suddenly began looking, and he thought first that he made element 93 and element 94 and announced it to the world, and it was really quite a great sensation. I remember I wrote about it at the time. There was man finally continuing the work of the Creator that stopped at the beginning of the world. But the trouble started when instead of just 2 or 3, there was a whole slew of new elements that were never observed in nature, much too many than they were expected. What is more, those elements were like cosmic anarchists that did not behave in any way that natural elements should behave, because you can predict how elements should behave. And so it became a puzzle, and the whole world of science wanted to, were attempting to solve this puzzle, but the more attempts were made, the more puzzling it became. And finally we come down to the year 1938, and there in Germany, a team of 2 men, 2 chemists and a woman, a physicist called Lise Meitner, And the chemist's name is Otto Hahn, the leading member of the team. Otto Hahn, one of the world's greatest chemists. And his assistant was Professor Fritz Strassmann. I met them both. And the lady, the woman, was the world's greatest living woman physicist. Her name was Lise Meitner. Many of you undoubtedly have heard of her. Now, Lise Meitner had a strange history. Lise Meitner was born in Vienna of Jewish parents, but was who had changed their religion to Catholicism, so she was a Catholic. And she had worked all her life in Germany with Otto Hahn. Together they discovered an element called protactinium, which is element 91, which is the element just before uranium, and made together, she as a physicist, he as a chemist, they made a great team, each one really making the contribution that each specialty provided. But when the time came around about in March 1938, Hitler had annexed Austria, Lise Meitner's native land. Now, until then, when Austria was still independent, Lise Meitner had an Austrian passport, and though she was under the Hitler basic Nazi Aryan racial laws, though she was an undesirable person, because she was an Austrian, they didn't bother her, they didn't touch her. But as soon as Hitler annexed Austria, she became homeless, both in a physical and in a spiritual and in a scientific sense. So the experiments she was carrying on at that time with Otto Hahn had to be discontinued. She escaped from Germany with the assistance of her colleagues in Holland, and from there she went to Sweden and continued her work. But in the meantime, Otto Hahn, with whom she had worked for 30 years, Otto Hahn continued communicating with her all the time, writing to her, telling her about his experiments, and she giving him suggestions and advice. So the partnership, in a real sense of the word, continued. And so one day in 1938, Hahn and Strassmann, working along in their laboratory in Berlin, Germany, it was about a few days before Christmas, began analyzing some of the products in their crucibles, in their chemical apparatus, and to their great amazement, they discovered elements in there which didn't have any right to be there. Elements they never put in there at all.
I can imagine
Elements
their
weren't there in
astonishment.
existence. Now I'll give you an analogy of that. Supposing you were running a hatchery, let's say, and you had duck's eggs. You were hatching ducks, and you put in a huge duck's egg in your incubator. And in due course of time, you expect, of course, a duck to come out, and out would come, let's say, something like a flamingo. Well, you'd be surprised, wouldn't you?
Certainly would.
Well, I'll tell you that to a chemist, the same thing happened. It was the equivalent of a flamingo coming out of a duck's egg. Because what Hahn found, Hahn had started with uranium in his crucibles. To his great amazement, he discovered a radioactive form of barium. Well, barium is an element about half the size of uranium in atomic weight. Uranium has 92 protons, positive charges in its nucleus, and barium has 56, nearly half, a little more than half, rather. So it couldn't be. How could barium come out of uranium? Nothing like that had ever happened before, any more than a flamingo could come out of a duck's egg. So he immediately communicated it to his old friend and collaborator, Lise Meitner, who was then in Stockholm. And Lise Meitner, of course, was very much puzzled too. She said, maybe it's a mistake. Maybe it was a contamination in your crucible. You better do it again. So he did it again, did it again, did it again, again and again and again. Each time out came the flamingo, or you might say the chemical flamingo.
Yes.
Well, that was fantastic. So all Hahn did was to write an article for a scientific journal to say that he observed that he put uranium in his crucible, that he fired it with neutrons the same way Fermi did, that he bombarded it with neutrons, hoping to create a heavier element than uranium. And instead of that, found elements, an element like barium, which was only a little more than half the weight of uranium. How it happened, I don't know. All I can say is, as a chemist, I can tell you that's what happened.
Mhm.
I've done it again and again, and there was the barium. But how it came there, I cannot tell you. So he told it to Lisa Meitner, and Lisa Meitner immediately dashed over to Copenhagen to the laboratory of the famous Professor Niels Bohr, who is one of the world's greatest living physicists, and told him the story.
Yes,
And
indeed.
in that laboratory of Professor Bohr was a nephew of hers, a young exile called Dr. Otto Frisch, and she told him about it. And she said, there is only one possible explanation for this, and that is that the uranium atom was actually split. But that was something unthinkable. It was something unheard of. It never happened before. So they said, well, if that is true, then she and Bohr and Frisch said, we can do an experiment, because we have an atomic thermometer, an atomic thermometer, which is in the nature of a television tube, the same principle, called an oscilloscope. And an oscilloscope measures the energy released in atomic bombardments. And so if the uranium atom was actually split, then a tremendous amount of energy, 200 million electron volts, should be released. They could calculate that. And if that amount of energy is released, it should be registered on this atomic thermometer, just the same way as the mercury, if you drop it in hot water, would immediately go up to 212. This would go up to 200 million. So Bohr was all excited. He wanted to do the experiment, but he was supposed to go to Europe, to America, to visit with his friend Einstein in Princeton.
Mm-hmm.
And his train his boat was leaving on the 6th, and this was the 5th of January. So they practically had to carry him bodily to the railway station and push him on the train to get him on the boat in time.
That's scientific enthusiasm,
Yeah,
isn't it?
enthusiasm. And in the meantime, Meitner and Frisch promised him that they will perform the experiment.
Mm-hmm.
Well, he got on the Drottningholm, which was a very slow boat. It takes 10 days to cross the Atlantic. And he got there on January 16 and immediately went to Princeton. But instead of going to visit his old friend Einstein, he went to see his old pupil, Dr. Wheeler, whom he told his story. And then Wheeler spread the news all around, every other place. And so by that time, Fermi had come again. Fermi had won the Nobel Prize and had gone to Columbia University, where he was continuing his work in a free atmosphere away from fascist Italy. And so Fermi heard about it. And so Fermi said, well, we will do the same experiment in this country. So he did, and sure enough, they did it in Columbia University in January 1939. Now, the story that, to point out, the fact is that Hitler's evil racial doctrines caused Lisa Meitner to be exiled from Germany, and she was in the free world, therefore could tell the world of the discovery, whereas if she had been left in Germany, they could have kept it a secret, and would have had the secret because that was the secret of the atom bomb, as it turned out later. So the world really was saved
Certainly
by the fact, by Hitler's evil laws. I don't mean to say that's excusable,
sure.
but as a result of that, out of evil came a good. And so Fermi started working. He said, no, we can probably harness this new release power into a plant that would produce the greatest amount of energy man ever produced, and will give the world a new source of power such as it had never dared dream about. The things now that we are talking about in Shippingport, like this plant here, and the others. So Fermi started working, and that brings us up. It took very slow work because it took money. He didn't have any money. He was a foreigner. He couldn't get anybody to understand him, really. Support him. But finally, after a long uphill battle, we find him at the University of Chicago on a cold winter day in a squash court underneath the west stands of Stagg Field, the University of Chicago. And there they are building a strange contraption with black bricks made of graphite. And the bricks go higher and higher and higher and higher. And inside the bricks they put chunks of uranium. And as more uranium is put in, the Geiger counters begin clicking away, clicking away. But in the meantime, men don't realize, they don't know how it will work out. They don't know, they're not sure that when finally this atomic fire starts really going, whether it may not blow up the whole works, you know, and blow up the University of Chicago and everything, but still they had to go on. And they had faith in themselves, but they had young men standing there with buckets of chemicals to put out the fire. They wouldn't have had the slightest chance in the world to put it out, because if the reaction had gone wild, it would have taken millions of a second, much faster than any human nerves could react. But anyway, it didn't, fortunately. And so on December 2nd, 1942, about 12 o'clock, there were men standing there, only about 42 men, young scientists, 41 men and one girl. And they were standing there tensely listening to the Geiger counters as they started clicking away more and more, more and more. And finally Fermi said, boys, let's go to lunch. So they all stopped to work and went to lunch. Came back in an hour and they started, I call them the cosmic bricklayers. They started working again. And by the time, about 20 minutes past 3, Fermi gave the command like a man docking a big ship, you know, like docking the Queen Mary, bringing her into port. He tells the young man, pull out the control rods, you see, pull it out a little more, pull it out a little more. And each time he pulled it a little more, the Geiger counter started clicking more and more. Then he finally said, pull it out 1 more inch and she will be there, you see. And so young George Wilde pulled it out 1 inch and the Geiger counter started clicking away for dear life, faster and louder, faster and louder. And then the man said, well, there she is. That's the first atomic fire lighted on Earth. The first fire on Earth that did not have its origin from the sun. And then...
A very dramatic birth of the atomic age.
And then, what's his name? One of the scientists pulled out a bottle of Chianti and they passed it around. And they all drank a silent toast to the atomic age. And then one of the men, Professor Compton, Arthur Compton of Chicago, a Nobel Prize winner in physics, called up his colleague, President Conant of Harvard. And he said, Jim, he said, I want you to know that the Italian navigator, meaning Fermi, the Italian navigator has arrived in the New World. And Conant said, that was an unrehearsed, mind you, conversation in code.
Yes.
And Conant said, excellent, how were the natives? Meaning, was it in control? And he said, the natives couldn't have been more friendly. And so, after watching it for a while, Fermi said, all right, boys, let's go home. And so the atomic age began at 3:25 on the afternoon of December 2nd, 1942, in the cold, gloomy squash court underneath the stands of Stack Field, the University of Chicago.
That's really a fabulous story, Bill. There's a little more to tell after that time. Through the war years, very briefly, you were in on a great deal of that, weren't you?
Well, I had the privilege later of being invited by the War Department to visit all the secret atomic plants in Tennessee and in New Mexico and in the state of Washington, and to prepare all the reports on them. They were still top secret, mind you, but they didn't want to wait till the last minute. They wanted to be sure that they would have accurate reports on them to release after the bomb, after the whole thing was announced. And then I had the great privilege of being allowed to go to Los Alamos to see the assembly of the atomic bomb. And then I was allowed to fly with the bomb over Japan when it was dropped over there.
Remarkable.
And I was the one who wrote the official accounts.
That's really remarkable.
Well, it was not the pleasantest thing to see.
No, I'm sure
but
it wasn't.
You know, that was the way to end the war. It saved a lot of American lives. It also saved a lot of Japanese lives. It brought the war to a victorious end at least maybe 6 months or a year earlier than it would have been.
Yes.
And
now we've been able to turn this to more peaceful uses now, too.
And now we finally really can use this great power that had been locked up in the atoms of the universe, in the uranium atoms, since the beginning of time.
I notice one of the applications of it is your tie pin.
Yes, this is a scale model of the first atomic submarine, the Nautilus. The atomic submarine, the Nautilus, has gone around the world 3.5 times at speeds underwater as great as any vessel above water. And it did that with a little bit of uranium the size of a golf ball.
Yes, it's remarkable.
It traveled 60,000 nautical miles. That's 2.5 times
This is certainly
around
a
the world.
force
and
for
it took
good,
that much uranium.
isn't it, Bill?
Not only a force for good, for power, but it will also produce, with transmuting elements, creating new elements that have tremendous value in medicine, in biology, in agriculture, in industry. We can, with these elements, with these new radioactive elements called radioactive isotopes, we can really change the world.
Now, you
Make
know,
it into a better
in
world.
fact, this very year, Bill, we're going to have in the Pittsburgh area at Shippingport this reactor, which we
Yeah.
have this scale model on, and then our viewers are going to see this in more detail in some of our subsequent discussions. We're going to examine this in quite detail
Yeah.
to describe this.
It's a beautiful model,
isn't
isn't
it,
it,
though?
huh? Yeah.
Well, you know, this reactor is going to be going critical on schedule this year, 1957, at the Shippingport.
By going critical, of course, you mean that it will start burning.
It'll start burning.
Yeah,
It'll achieve the
Yeah.
development of
Yeah.
atomic power
yeah.
at this Shippingport location on the Ohio River, and will
Yeah.
actually be feeding something like 60,000 kilowatts of electrical power into the city and the environs of Pittsburgh. It's
Yeah.
truly going to be a remarkable thing.
Well, that's the first of its kind, but that's the beginning. In another 10 years, we shall have all kinds of plants of different designs all over the country.
Bill, I'm sorry, but I'm going to have to interrupt you and tell you that the viewer and I have really enjoyed your talking to us. We're very pleased that you could come
Well,
visit.
I was...
And we hope that our viewer is going to come and be with us on our next discussion period, when we're going to continue in the application of nuclear energy. Until then, thank you.
Nuclear Energy, Key to Tomorrow. Produced by WQED for the Educational Television and Radio Center, in cooperation with the Westinghouse Electric Corporation and the Atomic Energy Commission. The subject, history. Your host, Dr. Warren Witzig, Manager of Reactor Physics. Special guest, Mr. William L. Lawrence, Science Editor of the New York Times. Technical advisor for the series, Mr. Edward R. Sanford. Engineering supervision by Frank Stuckman and Steve Zorbas. Production and direction for the series by John W. Ziegler and Robert E. Potts. This is National Educational Television.